Welcome everyone. So, in the previous lecture we discussed about mass spectrometer, the basic principle of it, different component of the instrument, and also we discussed about the resolving power, efficiency and abundance sensitivity of a mass spectrometer. In addition to this basic principle, when you really measure an isotope, what happens is it has to go through various kind of corrections. Something like if you put a sample and heat it, there are a lot of instrumental fractionation that happens, and also you have to make certain background corrections. So, these are some of the aspects which we will discuss today. So, if you let us say your objective is to find isotopic ratio for one rock sample. So, you got a rock sample and you want to look for the isotopic composition of this rock for an element. Let us say that element is strontium for the time being. We have been discussing about strontium because in the subsequent lecture we will see that strontium has been extensively used for various earth science problem and oceanic problem. We will discuss those things. If you look for this strontium, as we discussed in the previous lecture, there are 4 natural occurring isotopes: 88, 86, so 87 strontium, 86 strontium, 84 strontium. They have varying degree of abundances like 0.5%, like 10%, this should be around 7%, and the highest is 88, this is like 82.5%. Now, this is the normal isotopic abundance for strontium, and this do vary for samples to sample. The main reason why it varies is because there is a decay term 87 rubidium, which through beta decay produces 87 strontium. So, because of this rubidium decay and age of a particular rock, the isotopic ratio for strontium isotope may change. So, people then try to investigate what is the precise isotopic ratio for any of these samples, and they report that in terms of a isotopic ratio, let us say 87 strontium by 86 strontium. So, this is the isotopic ratio which is used to represent the isotopic ratio for strontium. So, now how do you analyze it using a mass spectrometer to find what is the 87 strontium by 86 strontium ratio in this particular rock? For that, what you need to do is when you are looking for strontium isotope, you have to purify that rock to extract the purest form of strontium that is lying in that rock. So, what you need to do is you take the rock, powder it and dissolve the powder using multiple acid. The frequently used acid are like HClO4, HF, HNO3, HCl. These kind of various acids are treated so that you get a complete dissolution of the rock and you get a solution phase. After you get the solution, what you do is you follow a chromatographic approach. So, what you do, you take a quartz column. In that you put a cation exchange resin, and after this you put the solution. You have to follow a medium, let us say in some form of HCl, let us say it is 2 normal HCl. When you do that, what basically will happen is this cation exchange resin, which are often in the H plus form. So, there are labile H plus which is lying here, and this solution when it pass through this, what will happen that they will replace this H plus and retain the cations that is there in that solution. and you can check for these solutions, and when you look for volume and concentration of samples, initially all the cations will come out of the solution at different phases. Let us say this is sodium, this is potassium, let us say this is rubidium, let us say this is strontium, you will have a calcium somewhere. So, what you need to do is you have to calibrate this column to extract or know what is the exact volume in which the pure strontium is coming, and you need to collect this pure form of strontium which can be used for isotopic analysis. I will repeat again. So, first you take a rock, prepare a solution phase, you have a column, and in that column you know what kind of, so basically you have to standardize this column depending on its length. What will happen at a particular volume of acid, when you are pouring this acid at a particular volume, this strontium will come out, the retention capacity will allow that, when it will come will depend on the distribution coefficient of strontium. So, at certain volume the pure form of strontium will come, which we will use for isotopic analysis. Alright, now that you have pure strontium, and when you try to do the isotopic measurement, so you take you can do that using thermal ionization mass spectrometer or inductive coupled plasma mass spectrometer. We will focus here on thermal ionization mass spectrometer, which is a solid source, and for that what you need to do is you take a filament and the pure strontium fraction you just dry it over the filament. So, basically this is the pure strontium, and in this strontium you have 84, 86, 87 and 88 isotopes in this sample. Now, you are interested to find out what is the 87 strontium by 86 strontium in this sample. So, first thing what you need to do is you apply temperature so that it get ionized. Now, during the ionization process what happens is all these isotope does not behave uniformly, they go through mass dependent fractionation. What is mass dependent fractionation? So, if you see the interatomic distance and potential energy for some of these atoms, so that should follow something like this. So, what happens is each of these isotope, if you try to understand the 0 point energy for all these isotopes, we know that 0 point energy is half h nu, nu is the vibrational frequency and this vibrational frequency is higher for low mass atoms. So, if you try to see in this plot, so the low masses should fall here, whereas the heavy masses should be shallower. So, what is happening is if you want to ionize it, basically you are trying to give this energy gap so that they can, the chemical bond breaks. That means, the breaking of chemical bonds within the low mass atoms is more readily doable compared to the heavier isotope, that leads to a mass dependent fractionation. So, when you measure a particular stable isotope in a mass spectrometer, let us say you are measuring a stable isotope 86 strontium by 88 strontium. Remember, this ratio is very different compared to the 87 strontium by 86 strontium, because there is a radiogenic part involved. So, we are interested in finding out this, but in case of stable isotope we know that the value for this is 0.1194, this is the true value for 86 strontium by 88 strontium. But when you measure and try to record that overrun period for any given sample, you will realize they start always with a higher number compared to 0.1194, and this higher number comes because chemical bonds of the lower masses are more readily breakable. So, after certain time this will decrease. The main reason that it decreases is because of a reservoir effect, where the 88 strontium, the amount of 86 strontium that is loaded will reduce. So, 88 will come. Now, to get a right number or the true number, which is 0.1194, you need to make proper correction for these sample runs. If you do not do that, then you may end up having a less precise isotopic data. Now, this instrumental fractionation can be order of 1%, whereas you are looking for a precision of ppm level, 10 or minus 6 level. So, you can't afford to leave it as it is. So, you need to make proper mass fractionation correction. And how do you do it? So, there has been studies to understand how this instrumental fractionation occurs in different instruments, and the scientists have realized they can follow a linear trend. At some point of time they can follow power law, they can follow exponential law, and accordingly you have to make corrections. But for today I will refer that this is following a linear trend, and accordingly we will make necessary corrections. So, this fractionation mostly follow Rayleigh mass fractionation, and which we know R0, the observed data will be RT, which is the true value. R I am referring here as an isotopic ratio, and R0 is the observed number which you are measuring, and RT is the true value. For this case it is 0.1194, and this is 1 plus F into delta M. So, this is the equation. What here we mean is, this is observed isotopic ratio, this is the true value of the isotopy ratio, F is the fractionation factor, and delta M of course is the mass difference. In this case the mass difference is about 2, it is not exactly 2, because you have to take care of the atomic masses and subtract. So, that should be about 2. So, if you try to do the same thing for F, if you write this equation for F, this should be like R0 by minus RT divided by RT 1 by delta M, right. So, if I write the same equation for 86 strontium by 88 strontium, then this will be F is equal to 86 strontium by 88 strontium, the measured one, divided by the true value, we know this is 0.1194 minus 1 divided by delta M. Delta M is about 2 here, basically 2.003. So, this is the F value. Now, when you want to find exact 87 strontium by 86 strontium true value, what you have to do is, you have to basically take R0 means 87 strontium by 86 strontium, that is measured, right. Then divided by 1 plus F into delta M. So, this is what you have to do. Now, this is the true value which you are interested in. To find that, you have already measured whatever 87 strontium by 86 strontium, you take that value 1 plus divided by 1 plus F. So, the F comes from this normalization, the fractionation factor, where you have normalized 86 strontium by 86 strontium to 0.1194. After that, you will find the true value of it. So, basically the mass fractionation what has happened, that is now corrected, and instead of the variation of about 1% due to instrumental mass fraction, after this correction you will realize that the precision goes up to 0.01%. So, this is what is done for mass fractionation corrections. So, we discussed till now that if you have to find a precise isotopic number, what you are doing is basically you are taking the sample in its pure form, then you are doing the proper background correction, right. So, every instrument has its own noise and you do the correction before you get to the correct answer. Then we discussed today that you do mass fractionation correction. But all the instrument, let us say you are talking of mass dependent fractionation, instrument like plasma, the inductive coupled plasma mass spectrometer may not require this mass fractionation as such, but they may go through something called instrumental fractionation. And these fractionation can be because of the continuous pumping that is going on, the slits that is there, they can remove a certain fractionation of it, and in that case there are various kind of fractionation which occurs in a inductive coupled plasma mass spectrometer, and you need to correct for those things. They are slightly different compared to the mass fractionations. So, in that case what you need to do, you do something called standard sample bracketing. So, because before sample you are running a standard, you know what is the true value based on the standard number, and whatever you are measuring in the sample you can correct for that, so that you can take care of any sort of instrumental fractionation that is occurring in a inductive coupled plasma mass spectrometer. Let it be a mass fractionation, let it be a physical removal through pumping, or because of disturbances created because of slits. So, those all things can be taken care when you are dealing with the standard sample bracketing, and that is the way you get the isotopic ratios which are precise to the order of 10 ppm level. So, this is how you do. But most of the time what happens, particularly when you are interested in a geochronology part of it, we are also interested to know the concentration of the same sample. Let us say you are measuring rubidium or strontium, you can measure the isotopic ratio in a mass spectrometer, but you also need for your scientific purposes the concentration of that, and a mass spectrometer does not give you that concentration term, mainly because during the processing you lose quite a bit of sample and you cannot quantify that. For to give you an example, you take a rock, this is the rock powder that you dissolve, you prepare a solution, this is expected to be 100%, okay. So, you may not lose out anything. So, you can do a good job and you can completely dissolve the rock to prepare a solution. Now, after the solution, when you are doing the column chemistry, the chromatography to extract the pure strontium, you may not get the, you actually does not get 100% efficiency. The efficiency can vary depending on what kind of calibration you are making. It can be of the order of 60% to 70%, because sometime you compromise that any sort of interfering element should not come, like the rubidiums or the calcium, you do not want them to come when you are doing the mass spectrometer, because they can create for a proper isotopic analysis, they can interfere, and presence of calcium can create problem in burning the rubidium. So, that is why you do not want calcium and rubidium. So, when you are doing the chromatography, you ensure that it is fine to get less strontium, but you target to get the pure form of strontium. After pure strontium is put in the machine, you have something called ionization efficiency, right, we discussed in the last lecture, and that can be like of the order of 1 to 2%. Then you have a transmission efficiency, and then that is also 1 to 5%. So, basically if you see the amount of strontium that is there in the rock till reaching to the detector it is almost negligible, and because you cannot quantify this process, you cannot talk about the elemental concentration, because elements get removed, but the isotopic ratio does not fractionate. During this process no isotopic fractionation occur. So, you get a precise isotopic ratio, but you cannot quantify the concentration of that element. Now, if you have to do the elemental concentration, then the best what frequently used is you take the rock, you measure the isotope separately using a mass spectrometer, let us say TIMS, then you take another alicot of it, then do the concentration measurement using another instrument, let us say atomic absorption spectrophotometer. Now, because you are doing in 2 alicots, the errors coming from these can be of the order of the ppm, the precision, these can be of the order of 5 to 10%. Okay. But when you are doing a ppm kind of analysis, you want to have the concentration in the same alicot, particularly in case of geochronology, and you want to have a better precision at least of the order of 1%. So, for precise isotopic and elemental measurement, concentration measurement, you can rely on an approach which is called isotope dilution. So, what you do? You do not measure the sample as it is, but add a tracer into it, prepare a mixture and do the isotopic analysis in the mixture. So, basically till now what you were doing, that you were taking a sample and you are doing the isotopic measurement. And for that you are not able to quantify the change, the losses that is occurring on the different pathways. So, what you do now, you add a tracer to it, these are called sometimes spike. So, you add you had a sample, you add this tracer, mix it. Now, instead of measuring the sample, you do the sample plus spike, this mixer measurement. Now that you know everything, this tracer is created by you know all the details of its isotopic ratio, its concentration, how much is added, what amount of sample was there. So, during this calculation you can quantify precise isotopic ratios and also the concentrations. So, for this ratio, let us say we have a sample which we will call as N, and let us say we have a spike which we will call as S, and we have a mixer which we will call as M here. Now, if you are measuring the isotopic ratio for this mixer, the mixer equation R M will be the isotopic ratio of A by B. So, let us say the A is an isotope, B is an isotope, and you are looking for their isotopic ratio in this mixer. This will be, so these are basically isotope ratio are basically the number, these are number of atoms that is there. So, if you do that, abundance of A in your sample multiply by the number of atoms that is there for N plus, because now this is there in both sample and spike. So, this will be like abundance of A in spike divided by total number of spike that is there, then divided by abundance of B in N multiply by N plus abundance of B to S into S. Okay. Now, let us simplify this. So, R M abundance of B N into N plus abundance of B S is equal to abundance of A N plus abundance of A S into S. So, let us write an expression for N. So, if you write an expression for N, that should be equal to So, basically what I have done is, so I have n is common in two terms, Rm ABBN minus ABN is equal to ABAS into S minus Rm ABBS into S divided by this term. So, this is the term for number of atoms of the sample is there in this mixture. So, if you can take the S out, so this will be like ABS S minus Rm ABB S divided by Rm ABBN minus ABAN. So, this is the final expression, but this expression, so there is a mistake here. So, this S should go out, we have made it common. So, this should go out. So, this is an expression for number of atoms. Now, we are not interested for number of atoms, we are looking, when you are looking for elemental concentration, you want to know how much gram of it of an element, or how much microgram is there. So, that you can, so the weight term can be written as n into Wn by A. What is here? Nw is the in weight term the number of atoms that is there, this is in by number, this is by weight, is equal to n into atomic weight of the sample divided by Avogadro's number. So, similar thing if you want to write SW, it will be n into Ws by A. So, these are actually atomic weight terms. So, this is atomic weight for sample, this is atomic weight for the spike. You know, because they have a distinct isotopic composition, their atomic weight will be different. To give an example, let us say rubidium has two isotopes, 85 rubidium and 87 rubidium, right. So, when you look for natural, that means what you expect in your sample, and spike which is artificially created for your isotope dilution purpose, in that spike you always enrich a particular isotope which will not influence the natural signature. So, if you see the typical abundances, this is 70, whereas this is 27.84%, and if you see the spike, this is 0.60% and this is like 99.4%. So, basically if you see the isotopic abundances, the 85 rubidium is only is about 72% in your sample, which is only 0.6% in your spike, whereas in case of your 87 rubidium, which is 27.8, it is the lesser abundant isotope in the rubidium system, but you have created an artificial spike which is enriched in 87 rubidium. So, if you try to look for their atomic weight, so this will come around 85.4677, whereas this will come as 86.8971 AMU. So, there are differences which is happening because the abundances are very different. So, that is why you have to retain this Ws and Wn differently, because they have different numbers associated. You cannot consider them as same. Now, let us replace these terms in here. N is Nw multiplied by A divided by Wn. So, here N is Nw multiplied by A divided by Wn, whereas S is Sw divided by A divided by Ws, then the remaining term. So, I have just written what was there. So, in this A and A cancels out. So, if you are interested in Nw, the final term for that will be Sw divided multiplied by Wn by Ws multiplied by abundance of A in the spike minus isotopy ratio in the mixture, abundance of B in spike divided by isotope ratio in the mixture, abundance of B in the natural system like your sample minus abundance of A in your sample. So, this is the expression which will give you the concentration for a given sample. We will do a numerical based on this expression, how people extract the concentration information using this expression of isotope dilution. So, let us say you have taken a 0.25 gram of a rock, okay, it was a rock, and then you dissolved it to 50 grams. So, basically you have a solution of 50 gram where it is have a 0.25 gram of this standard. In this you added a spike, we are talking for rubidium. So, this spike is enriched in 87 rubidium with a concentration of 7.5 microgram per gram, and you have a solution of 87 rubidium spike, and you added to that to this solution which contains 50 gram of the rock solution, right. So, in that out of this solution you just added 3.5 gram of spike. Okay. Now, you had a 50 gram of your sample solution, in that you added 3.5 gram of spike. So, you have the spike is 87 rubidium enriched one, and the concentration of this spike solution whatever you have is 7.5 gram. Now, we know the abundances or so I am writing the natural on spike abundances here. So, if you look for 85, 87, these are the isotopes. So, the natural isotope is 72.16%, this is 27.84%, this is 0.994%. So, if you see the atomic weight term, so this will come around 85.4677, this is coming around 86.8971 mu. Okay. Now, we will use this equation, Nw is equal to Sw. Sw is 3.5 multiplied by 7.5, which is 23.5 multiplied by 7.5. This is the total microgram you have taken, multiply by Wn, this is the Wn 85.4677 divided by then Ws, the spike atomic weight is 86.8971, and these two are different, that is why you are taking two different terms, multiply by abundance of A in S. Okay. So, this is when measured, this Rm was 1.55. The mixture of these two was measured, the ratio which is 87 rubidium by 85 rubidium, the ratio is measured as 1.55. So, the abundance of A which is 87 in A, 87 in sample, this should go 0.994 minus ratio, this is 1.55, abundance of B 85 here, 85 B is 0.006 divided by ratio is 1.55 multiplied by abundance of B which is 0.7216 minus A is 87, so it is 0.784, right. If you solve this, I have already solved this, and this comes around 30.25 micrograms. Okay. If you solve this, you will get some term like 30.25 gram. Now, this is the amount of sample that is there in the solution, but the solution is 50 gram. So, in the 50 gram you have this much of it. So, what is the solution for then the concentration of rubidium in the solution (30.25) divided by 50, that comes 605 micrograms. So, per gram, right, micrograms. So, in this solution, if you are interested, then the concentration of rubidium in the solution is 0.605, but our ultimate aim is to find the concentration of rubidium in the rock, which is 30.25 divided by 0.25. 0.25 gram is the rock. So, this has to be 121 microgram per gram. So, this is how you will get the concentration of a rock using isotope dilution. Now, the major challenge is, one thing that now we need to understand, that when you are doing this isotope dilution, we are basically adding a sample in a spike. But the major question is, how much sample or spike has to be added in a sample? That is something very important. If you do not add the amount of spike precisely, then you may end up having a over spiked mixture or a under spiked mixture. In that case, you will not get a precise number. What do I mean by under spike or over spike? So, when you are measuring the ratio in the mixture, and if you try to see the error associated with that, there is only, if you see the trend, it goes like this. So, there are certain zone only where it can give you low error, but the other places it can be, if it is under spiked or over spiked compared to this zone, then it may be very difficult to find a very precise number. Typically, isotope dilution, the concentration errors are about 1 to 1.5%, and you want to achieve that. When you want to do that, what you do is the mixture ratio you have to maintain in such a way that it should be a ratio of sample and spike. This kind of, so if you are looking for rubidium, let us say, so you have to take care that the 87 rubidium by 85 rubidium in the spike plus 87 rubidium by 85 rubidium in your sample, addition and the square root should be the 87 rubidium by 85 rubidium in the mixture. So, you should target to have a mixture ratio around this number. If you cannot do that, then you may end up in this direction and that direction, and hence you may not get a precise number. So, you have to take care that the right amount of spike is added to get a precise concentration data using isotope dilution. Thank you.